In this video we're going to talk about the isochoric process, and isochoric means constant volume. This usually happens when we have a rigid container, and the process looks, for instance, in a PV diagram as a straight line where we go from point 1 to point 2, well, in a certain direction. And given the fact that the work is going to be the integral of PdV, that's the moving boundary work, or the area below the curve, since the boundary is not moving, it's a rigid container, there is no area below the curve, the work here is zero. This fact states that since the first law, heat minus work equals change in internal energy, if there is no other external law work, for instance no electric work, well, this will go to zero, and the first law will be that the heat is going to be equal to a change in internal energy. The change in internal energy might be quantified as in tables. For instance, if we have water and refrigerant, we can go to tables and we can find the change in internal energy as U2 minus U1. So in this case, it is going to be the change in internal energy, but we can also define a specific heat at a constant volume, which is given, for instance, by definition, by the change in internal energy with respect to temperature when the volume is constant. So from here we can define as well that the differential of internal energy is going to be equal to the specific heat at constant volume, Cb, times the change in temperature, and if we do the integral, well, the change in internal energy, this could be specific, this is a specific internal energy, it's going to be equal to the integral from temperature 1 to temperature 2 of Cv times dt. And Cv, in table A2, you can actually find the values for different substances. Now beware, because these are at 300 Kelvin, and well, the Cv changes with temperature. So we have other tables, for instance in A2. This is, for instance, a table that shows different values of Cv at different temperatures, but more complete is this one. This one shows, for instance, Cp, and we're going to talk more about this in a later video, but this is a function of a function with respect to temperature. And how can we go from Cv to from Cp to Cv? Well, it is very straightforward. So, for instance, in order to get Cb, and is going to be equal to Cp minus R, the constant. Now, beware, because this table is only working, for instance, when the temperature is at Kelvin, and Cp will give you at kilojoule per kilomole Kelvin. So how can we work with this? For instance, let's take the first one, which is nitrogen, and if I want, for instance, delta U, this is going to be equal to the integral of Cv dt, which, for instance, is, let's take whatever, it's a function of A, so this is going to be A minus R, which is 8.314, because we're working in kilojoule per kilomole Kelvin, plus Vt plus Ct to the square plus dt to the cube dt. And then we can do the integral, right? So for instance, we will have a minus 8.314 times t plus the value that we have of b over 2 times t squared plus c over 3 times t to the cube plus d t to the 4th over 4, and well, this is going to be evaluated from t1 to t2 because this is a defined integral. So this is going to be, for instance, a specific delta u, which, given the fact that we are working with the first law, well, this is the heat in an isochoric process.